All right, chapter 11 is about vectors, and we're going to look at a lot of different properties and concepts related to vectors. Today we're just introducing the idea. So these are vectors in the plane. And just kind of some terminology. So this is all written in a big old fail swoop because this is sort of developing the idea. So when we describe velocity, and some of you are physics people, so you know more about velocity than I do. When we describe velocity, we describe velocity in terms of speed and direction, right? And so vectors are related to that idea. So we represent such a quantity graphically. For us, what we're going to do is a directed line segment. And a directed line segment looks like a ray. So from geometry, you're looking at something that starts with one point and it has an arrow on one end. So it looks like this. We denote the directed line segment by extending from the initial point P to the terminal point Q. And we write it as PQ with the ray notation on top of there, just like you're used to seeing from a geometry perspective. We refer to the length of PQ as its magnitude. And it's denoted with these double bars. Looks kind of like an absolute value symbol, but it's double bars on there. And we mathematically consider all directed line segments with the same magnitude in the same direction as equivalent, no matter where they start. So if I were to take this directed line segment that I've drawn on the board here and I were to move it over here, as long as I didn't change the angle that it's pointing to or the length of it, we would call that as the same vector. Okay? So I already used the word twice now. Regardless of their initial point, we use the term vector to describe any quantity that has both magnitude and direction. What we're doing with this section and how vectors work is pretty easy to work with. And so instead of sort of giving you a lot of descriptions about how to apply things, I'm just going to show you how to do it because it's going to make a lot more sense in the context of an actual example. Okay? So that's the first example we're going to use. Is everyone close to finished with the writing? Are you good, Ben? Okay. So here's our example. We have different things that we're supposed to compute, and we've got two vectors. So there's a couple of ways you can see vectors written. One of them is written sort of like ordered pairs, but you have these angled brackets around them. Another way that you might see them written is with components I and j. So for instance, this vector A could be written as 2i plus 4j. And we'll see an example where we've got something written that way as well. So those are a couple of different components. So the I component is the horizontal component. The j component is the vertical component. Right? So we're going to take this example then. I'm not going to erase this one because I don't need that piece of information there. And we're going to find several things. So the first one we're going to find is A plus B. So without me telling you how to do this, what would you think that A plus B should be?
5, 3.
Okay, so tell me how you got that, Cameron.
The x's, add them together.
Mm-hmm.
Y's, add them together.
Right. And that's exactly what it is. You're just adding component-wise. So this ends up being the vector 5, 3.
Do you want us to write it like that, or could we use the IJ notation?
You can use the IJ notation. I don't care. Whatever you feel comfortable, it's fine. We'll do the next one. So the next one is A minus 2B. So what's that going to do? What am I going to do different? What do you think, Nidra? Exactly. So everything that's in the B vector, I'm going to double it. So it's going to look something like this. I can take the component that's in the A vector 2, and then I'm going to subtract 2 times the component in the B vector 3. I can take the component 4 and subtract 2 times the B component 1, negative 1 rather. What does this give me? Negative 4, 6. The part that I'm writing in the middle, if you don't need to see that, don't write it. I don't need to see that you've written out 2 minus 2 times 3. I don't have to see that. I just want to make sure everybody's seeing where we're getting these values at the moment. Okay. What about 3a? What am I going to do for that?
That'd just be like 6, 12.
Right. So I'm going to just multiply 3 times vector a, which is 2, 4. So Joel's exactly right. This becomes the vector 6, 12. And the last one's a little more complicated because it's asking about magnitude, right? So before I actually do magnitude, let's just find out what is vector 5b minus 2a, because we haven't done that part of it yet, and then we'll find the magnitude of the result, okay? So what do I do to find 5b minus 2a?
Do it.
So there's a 5 we're going to be multiplying by. 5 times the component b, which is in the x value, or the first location is the value 3, minus 2 times the coordinate in the first location for the a vector, which is the value 2. And then I have 5 times negative 1 minus 2 times 4. So somebody tell me, what vector do I get when I do this?
11, negative 4. Negative 6 minus 6 is negative 12.
I think it's negative 5 minus 8, though, right? Negative 5 minus 8. So maybe negative 13. It's okay. It's Monday, right? Okay, is everybody good with 11, negative 13 on that one? All right, so I want to give you a visual for why magnitude is what it is. And so imagine what's going on here. I haven't actually drawn you a vector in a coordinate plane yet. So I'm going to use the next slide, and I'm going to draw it, and then I'm going to erase it because I need this slide for something else. But we've got this vector that's 11, negative 13. So what we actually have is we have an x value of 11. Caleb, man, you're just totally spoiling everything. So we're going right 11 and we're going down 13. And if I've measured this correctly, we're somewhere about right here. And so the directed line segment actually looks like this. So this is my vector, okay? And what I'm actually trying to find out is I'm trying to find out how long it is. And so Caleb, what did you say we're going to do to find out how long it is? Yeah, we're doing the Pythagorean theorem, so we're making a triangle here. So we've got this distance right here, which is 11, and this distance, which is 13 in essence. And so the magnitude is actually the Pythagorean theorem, or the distance formula, if you think about it that way. So back over here, when I'm finding this, after I have found the vector, finding the magnitude of any vector is simply taking the square root of each component squared. So this is 11 squared plus negative 13 squared. What do I get underneath my radical when I take 11 squared plus 13 squared? 290. And we would try to reduce that if we could, to see if it simplifies any. This one actually doesn't, because it's 29 times 2 times 5. All of those are prime numbers, and none of them is occurring more than once. So square root of 290 is the best we can do, so to speak. Okay, so is everybody good with the ideas behind vector addition? Vector scalar multiplication. We did some differences, and then we did magnitude. I want to show you visually, though. The last two parts of this problem tell us to find, or to illustrate a plus b and a minus b graphically. And so that's what I want to do on this slide over here, is to illustrate that graphically. And it would have been helpful had I drawn in some graphs like these beforehand, but I didn't. So we're going to make do. You guys use graph paper if you have it. So the first vector, A, is actually the component 2, 4. So we're going to actually write that in here. So the component x, or the sort of the x direction 2 and the y direction of 4, puts me at this location roughly. And my vector looks something like this. So this is A. And my goal here is to actually add A plus B visually together. So this would be like saying that I'm traveling along this vector A, and when I get to the end of vector A, I'm going to be taking a new direction and magnitude, new vector. The vector is the vector B. So I'm going to start the vector B where A ended. You guys with me? So vector A was 2, 4. What was B?
3, negative 1.
B is 3, negative 1, which means I'm going to be going right 3 and what? Down 1. So right 3 and down 1 puts me right here from the end of where A ended. So I'm going to be doing this. Right 3, down 1. Remember back on that first slide when I was describing some things, I said any directed line segment, if it starts somewhere else, is the same vector. So that's what I just did. I just chose to start my vector at the location where A ended. Okay? So this is vector B. It's not B shifted anywhere, it's just B, because B can be anywhere in the plane. So the addition of these two vectors is the result of having done what I just did. So I'll change the color here. This is the vector AB. I'm sorry, A plus B. Let me get the right language in there. And if you added it component-wise, you would see that it actually matches. So we did this a minute ago, and we got the vector 5, negative 3. I'm sorry, positive 3. And this is, in fact, what I've got drawn here, right? If I start at the origin, I go right 5 and up 3. So I end up with the same visual relationship that I had before. We're going to do the same thing now with A minus B. So same kind of a graph, but we will imagine doing the exact, I don't want to say opposite, but kind of. So we're going to go over 2 to the right and up 4. And here's my vector A. Oops. And then the vector B is supposed to go right 3, down 1, and we're doing the opposite because we're subtracting it. So instead of going right 3, we're going to go left 3. And instead of going down 1, we're going to go up 1. I mean, we're just changing the direction. You could also think about taking the vector B as it's drawn and sort of going in the opposite way. So we're going to be going left 3 and up 1, which puts me right here, roughly. So here is vector B. And again, the net result of doing that is going to be the resulting vector A minus B. So I'll do another color again too. We'll do blue. Right here is the vector A minus B. And again, if we were to take this component-wise, this wasn't one of the ones we calculated, but you guys could do it real quickly with me. What is A minus B component-wise over there with our values? Negative 1 and 5. And is it over left 1 and up 5? Yeah, that's where I ended up exactly, right? The coordinate pair. So this is a graphical sort of picture of what's happening. All right, let's move to the next idea about vectors. So two vectors that have the same or opposite direction are called parallel. That makes sense. The direction is exactly what's determining sort of what we interpret as a slope of something. The 0 vector is considered parallel to every vector. Kind of by default is the way that that's being described, right? It's not really got a direction, so by default it gets to be parallel to every vector. All right, so let me talk about in the next example then how we determine if two of them are parallel, because we don't really have a slope. And in fact, it doesn't even really make a lot of sense, because in order to create a slope, I've got to actually have 2 points. And a vector is not 2 points. It's sort of 1 point. So here's the way here's a way, at least, that you can determine if the vectors are parallel. So we're going to take vector B, which is 2, 1. And if it's parallel, it means that I should be able to multiply by a constant c by the vector A. So this is A. 1, negative 2. So if I take this, I'm going to get, c and negative 2c. Okay? It's just scalar multiplication. All I'm saying is that I can change the length of my vector by multiplying by c. And the length of the vector I'm wanting to manipulate is the other vector I started with. The question is going to be whether or not I can create this value c to have the same components. So we're going to compare these component-wise. In order for these two vectors to be equal, plus or minus multiplied by the scalar c anyway, I have to be actually create that c2 equals c1 and 1 equals negative 2 times c, sorry, not c1, c, not c1. Where's my eraser? Negative 2 times c. So obviously in the first one, I see that c is 2. What is the c value in our second equation? Negative 1/2. And these are not equal, right? So there isn't a way to create them. The basic idea is that in order for them to be parallel, I should have had to take one of the vectors and multiply them by some non-zero constant and actually create the other vector. And I can't do that. I tried to multiply one vector by some non-zero constant c and see if I could get them to match, and it doesn't work. So these are not equal, which means these are not parallel. And if you wanted to confirm it, what could you do? You could graph it. And you're going to see really quickly that if you start at a specific point in time, it doesn't matter really where you start, but that you're not going to get parallel directed line segments. They're not going to be parallel. All right, you have seen many of these concepts before, and you've got lines next to yours. I would like for you to take a look at these, take just 2 or 3 minutes, and see if you can remember what the operation is called. If you have pencil, write it in pencil, just because there is a couple of them that are a little bit different because it's vectors. But see if you can remember what property it is that's allowing things to happen. So the first one, A plus B is B plus A. We see that in a lot of what we do in mathematics. The second one is A plus quantity B plus C is the quantity A plus B times or plus C, and so forth as you go your way down. So see if you can fill in what's on the line on the right-hand side with what the property name is that you expect it to be. What property is this going on? Okay, so do your best. Give just a couple minutes to take a look at what you think. A couple things you might notice in how this is sort of typed together is, do you see on line V, number 5, how there's a script D and then there's the A and the B that are sort of bolded and not script? Do you see that? You notice that? What your book does, and this is a pretty common convention, is that if it's a vector, it does it in bold and it doesn't look slanted. And then if it's a scalar, now scalar just means a number, you're just multiplying by or adding or something, it will do it in that sort of a scripted looking, not bolded font. So what you see on like V and VI is you see some scalars involved with some vectors at the same time. In most of the other cases, except for, well, in the first 4, it's all just vectors, right? It's the vector A, it's the vector B, it's the vector 0, and so forth. Do you remember what number 1 is?
I have it in the book.
Close your book, Caleb. I'm going to show them to you, I promise.
No, but I was wanting to write them down because I only got one.
Does anybody remember what it is? Commutative, very good, Nidra. Yes, it is the commutative property or commutativity. Do you know what the second one is? That's associativity or associative, yeah. The third one's a little different than probably what you have written down. So what did you guys write down?
Addition by 0.
Yeah, sometimes when we do this with whole numbers, we call this the additive identity. Your book just refers to this as the 0 vector. And then number 4 is actually called the additive inverse, right? It's the opposite property. What are V and VI, number 5 and number 6?
I got this one.
What are they?
Distributed.
They are the distributive laws, right? One of them actually shows you if you have, and they are different because one of them's got 1 scalar and 2 vectors, the other one's got 2 scalars and 1 vector. But these are both distributive laws. The last 2 are different than what I would call them. Again, kind of like part 3, I would have said that's additive identity, but they're calling it the 0 vector. 7 and 8 have the same kind of thing going on. They're just calling it multiplication by 1 and multiplication by 0. So these are the different laws that you see happening here and the way your book is actually labeling them. They're not very exciting. They're exactly what you would expect and hope would happen. Tell me something you don't see here. That's a hard question because you don't see anything with division. There's something else you don't see too. Any other thoughts?
Exponent.
No exponents, okay.
I don't see an integral. I don't see a derivative. There's a lot of things I don't see.
The one that maybe is most glaring, and the reason it is because I know a little bit about vectors, is you don't see any vector times a vector. Do you notice that? And you don't see anything with division either, which is also a glaring sort of omission with what we've got going on. So, yeah, dot products and cross products, they're coming up in 11.3 and 11.4, I think they are. So we'll talk more about what happens when you try to do some sort of a multiplication idea with vectors, because it isn't clean and clear. It's not what you would expect, right? It's kind of like what happens when you first talk about addition and subtraction and doing derivatives and integrals. It's everything you'd ever want it to be. It's exactly what you would expect, right? But once you get to doing a derivative of a product, not what you would expect. You can't just take the product of each one and then multiply them, right? That would be nice, but it just doesn't work. You got kind of the same feeling of that when you're doing vectors. All right, let's take a look at some other examples of things we're going to work with vectors on. Here we're going to find a vector with an initial point and a terminal point, and this is very straightforward, very clean. Basically, you're looking at the change in what's going on here. So if it helps you to see a picture, you could do that. I'll draw a picture at the end. But let me just talk in terms of calculation first, and then we'll confirm with the picture so you can see how that works. All you're doing is you're starting with the terminal point. That's the -2 right here with the b. And you're subtracting the initial point value. That's minus this 1. And you're doing the same thing for the second component. You're starting with the second component 4, and you're subtracting the initial component 1. So you get the value -3. So let me take this in terms of a picture with the actual component values that we were given, points A and B. So if you're doing the point A is at 1, 1. And the point B is at -2, 4. Oops, I got too many lines in there. And you're trying to do a line segment that goes between the two. That was really a bad line segment. Let me try that again. How about that? So if you take a look at this line segment, this description of this vector talks about the direction of the line segment. That -3, what is it telling you? What does that -3 mean?
3 negative x direction.
And negative x direction would be like left, right? I mean, correct? So this means left 3. And this 3 would mean up 3. And take a look at my picture. Did I in fact go from the first initial point, left 3, and then from there up 3? Yeah, I did. And so that's visually what's going on and how it correlates to the description of the vector in component form. So if you want to memorize it or think about it from a component subtraction perspective, you can. If you want to think about it by drawing a picture, that works just as well too. I don't think you're going to be dealing with any ugly sort of numbers that you can't sort of visualize on a graph anyway, so that would work fine. Any questions on that? Okay. Caleb, there's your I's and J's. All right, so here's another form of a vector. I mentioned this earlier, that we've got this I and this J as a number 4. So again, if you want to change this to think about it like this instead, if you like that, it feels a little bit more warm and fuzzy, then you can. It doesn't matter. They're the same meaning, different notations. All right, so these directions are a little different. This one says to find a unit vector in the same direction. So let's imagine, let's say for instance that you had a vector and it was in this direction and it had length 5. Okay? So it's got some components with it, but the length of it when you did the Pythagorean theorem was 5. So, maybe it went 4 this way and 3 this way. That would give me a 5, so I could do that. How would I take this vector of length 5 and sort of shrink it down? What would I have to do to make it shrink? I mean, I don't want to change the direction, right? What would I do? Okay, so what would I do, like, mathematically to shrink them? Do you know? No, but you're getting closer.
Keep multiplying them both by the same number.
Okay, so we're going to multiply them both by the same number. What would I multiply them by if I wanted to make that 5 turn into something that is a unit of length 1?
You divide it by its magnitude?
Yeah. So if the length is 5, its magnitude is 5, I'm just going to divide by that 5. Or you could think of it like Jordan said, multiplying it by something, which would be multiplying by 1/5. So whatever the length is right here, you're exactly right, Brandon. This length has length 5. We're going to take that length of 5 and we're going to apply that to each of the components to shrink them down. It's division. This is exactly what the projector is doing on my board right now, right? It's taking something that's coming out of there this big and it's projecting it with those same dimensions on my screen. But I'm going to do it backwards. I want to make it shrink back down. So I need to find the magnitude. So let's find the magnitude. What is the magnitude of this 2i plus 4j? So you have the square root of 20. Is everybody okay with that? 4 plus 16, which is otherwise known as 2 square roots of 5, right? I'm going to delete this picture because it doesn't really apply to my diagram or my description of the problem we're working with. So this is 2 square roots of 5. So I want to take my components 2 and 4, those component forms, and do what? Divide them. Yeah, I want to divide them by 2 square roots of 5 or multiply them by 1 over 2 square roots of 5 would be fine as well. So I'm going to take 2 and divide by 2 square root 5. This is still I. And I'm going to take 4 and divide by 2 square root 5, and that's j. And now you're just going to clean that up. You know, rationalize when appropriate. You're going to reduce where appropriate, and there's both of those things going on in this one. So my 2's here reduce, my 2 and my 4 here giving me a 2 on top, and I'm going to rationalize. So what am I going to get on the first component, on the I component? Square root 5 over 5i. And then how about the second component? And it's j. Or you can write it in the brackets. That's fine too. I don't care. Let me just kind of warn you in advance, because you're going to see the answers that I use, or not use, but I have access to them in a post for you. You're going to be referencing those probably, hopefully, as you do your homework, right? So that you know that you're doing them correctly. Sometimes they don't rationalize, and I don't really know why. Most of the time they do, but there are places where they don't too. So you're just going to rationalize. I mean, there's no reason not to. You're perfectly capable of doing that. So on this one, for example, this is an example that, I don't know if it was even or odd, but I pulled it straight out of the textbook, and I was looking at the answers to see how you were going to see them, because you were going to see them this time, and they didn't rationalize this one. I don't know why. But the next example that I'm going to show you, they did. So I don't have a good example, a good reasoning for that, but just go ahead and rationalize when appropriate, okay? Any questions on this one? All right, there's a part B to this too. Part B says, write the given vector in polar form. Did you think you were done with polar?
Yes.
Oh my goodness. Yeah, polar is here to stay for a while. You're going to encounter it again in Calc 4 if you take that one. All right, so given vector in polar form. All right, so here I could kind of go into huge amounts of depth, but the idea of polar form is that you're looking at magnitude, length, right? And direction, as in angles, aren't you? That's kind of what we're already doing here. So the magnitude of this is 1. That's what I actually created. If they want the given vector, they're in polar form. So our given vector that we were given up here, what was its length? Well, it was 2 square root of 5. I mean, that was its length. So my original vector, so this is part B now, had an r value, if you will. The length was 2 square root 5. I don't actually need theta to find what I'm going to be doing, but recognize that when we're talking about an x, y kind of a description, what was x in polar form? R cosine theta. And what was y? R sine theta. So when we're taking a look at this, we're going to sort of, in essence, factor the r out in front, because it's in both components, and we're going to write it as a multiplication factor in front. So taking a look at what we're doing right here, this, let me move this up actually. This component that we're doing is going to have that r value written in front. That's that 2 square root of 5. And then what actually goes inside is the unit vector. Okay, so my unit vector was square root 5 over 5 and 2 square root of 5 over 5. So this is my unit vector. Because if I wanted to use the cosine theta, right, that's this piece, and the sine theta, that's this piece, I could use those pieces of information to find the angle, because this is another way of giving me my direction. So the polar form doesn't actually have any r's or thetas in it, but the rectangular form didn't have x's or y's actually in it either, because I'm given values, so that's why. We're going to have another polar form thing here in a couple of examples. I think it's number 6. Let's take a look at 5. Find a vector with the given magnitude in the same direction as the given vector. Okay, this is just an extension of the last example. What was the directions on part A of our last example? Somebody just read them out loud.
The what?
The part A directions on number 4.
Find a unit vector in the same direction as the given vector.
Okay, so what part of that says the exact same thing as this direction set? Same direction. So I want something in the same direction. And the way I get something in the same direction is because it has to be a scalar multiple of what I had before, right? So I either lengthen it or I shrink it. That's how I get the direction to stay the same. On the last example, I wanted the length, the magnitude, to be the value what? 1, because it said unit vector. This time I want my length, or my magnitude, to be a value of 10. So what would I do differently than the last problem? You're really close. Times the unit vector by 10. So I'm still going to get the unit vector just like I did before, but then after I've got the unit vector of length 1, if I multiply it by 10, now I'll have something of length 10. Are you guys with me? So this is sort of just an extension. It's one more step beyond what I did before. So first we're going to find the unit vector. And to find my unit vector, I need my magnitude. So let me write it this way. Right? That's the magnitude notation. So what is the magnitude of the vector 3, 1? Square root of 10, right? 9 plus 1, this is square root of 10. So if I were to find my unit vector now, my unit vector would be 3 divided by square root of 10 and 1 divided by square root of 10. This is my unit vector. It is a vector in the same direction of length 1. But I want to take that unit vector now and make it a vector of length 10. So my vector of magnitude 10 would be to take the number 10 and to multiply by the vector 3 square root of 10 over square root of 10 and 1 over square root of 10. Now this will actually be easier to multiply by if I rationalize first on this particular one, which is another good reason to do the rationalizing, at least on this example. So this would be 3 square root of 10 over 10 and square root of 10 over 10, right? So if I multiply 3 with the 10, what do I get for my vector of magnitude 10? Right. So basically what I'm doing is I'm taking something that has a given length and I'm shrinking it down so that it has a length of 1, and then I'm multiplying it by the value I want so it has the actual length that I'm interested in having instead of the original length it had. Okay, so the original length was 2, or was that square root of 10. I turned it into something of length 1, and then I multiply by 10 to get it being length 10. Does that make sense? It's all component-wise, too. All right, we're going to do another polar example. This time we're actually given the information with the r and the theta. So as I mentioned before, the basic idea is that this is r, and then it's a cosine theta, sine theta. That's what we're going to be doing. So what is my value for r? It's 2. And my theta will be plugged in. So I've got cosine of pi thirds, sine of pi thirds, and there's that unit circle coming into play again. So what is the cosine of pi over 3? Yes, it is. It's 1/2. And the sine of pi over 3?
Square root of 3.
Square root of 3 over 2. And that right there would be a polar form of the vector. It just says to find a vector with a given polar form. So we'll go ahead and multiply 3 with this. If you left it in this form, since it's not being clear, you could probably get by with that and not be a problem. Or you can go ahead and multiply. So either of these answers would be acceptable. This would be the polar form that we were looking at before, and this would be, they don't refer to it like this, but it's basically rectangular form. All right, any questions on that one? Okay. Here's our last example. This example says to sketch A, B, and C with the initial points at the origin. So they actually tell us they want us to start at a specific place. And then they want us to sketch a parallelogram with diagonals C and sides parallel to A and B. And then write C in the form C1A plus C2B. So we're just going to take it piece by piece and start with the part where it says sketch. Okay? That part you know how to do, and I've got a diagram shown for you because I thought that it might be easier than trying to visualize it, because when I drew it by hand it wasn't looking like a parallelogram. So maybe yours won't either, I don't know. But we're going to draw this with the points that we're given. So the first vector we're given is vector A, and it's the vector 2, 1. And I just drew the first coordinate because everything's positive on this one, so I didn't need the negative side or the bottoms or anything of that of the graph. So 2, 1 puts me right here. And this is my vector A. Whoops. Like this. So that's A. Vector B is 1, 3, which is right here. So that's B. And then vector C is 7, 11. So I think that's my 7. And I think that's my 11 right there. Even with the grid, I'm not doing so great. A straight edge will help you. So if you have something you can line up against what you're drawing, it'll help you to draw that one, because this one's longer, so it's going to be harder to draw it straight. The other two you probably could have done without any problem. But we're drawing this line segment here. Directed line segment. And that's C. I don't know about you, but visually right now there is no parallelogram to be seen. Agreed? Okay. But the idea is that we're going to take this vector A and we're going to make it a little bit longer. And we're going to take vector B and we're going to make it a little bit longer. And we're going to get a parallelogram. So we're going to create something visually, and I'm going to sort of sketch what it might look like, but not knowing exactly how far to go, that makes it difficult. But I'm going to do something so that when I connect this, I get a parallelogram. So obviously eyeballing this one was not such a good plan. I don't have anything, but you have the idea of what we're looking for, right? So let me show you how we actually go about finding how long or how far we extend these components. All right, so let's take a look at this idea that it talked about over here about the form of what it's going to look like in the end, because that form actually gets us the information we need to be able to draw the graph correctly. So we're going to take C1 times A plus C2 times B, and in a vector form, we know how to do that. We've done that since the very beginning of example 1 in this lesson. So we're going to take C1 times component A. So this is C1 times 2. In fact, I'll put the C in front, I think. Component A, so this is 2, 1. We'll write it this way for the moment. And then C2 times component B, or the components of B, which is 1, 3. You can distribute the C1 through. You can add the pieces together. All of that's just fine. If we do that, in fact, I think I'll show that. Why not? We're going to have 2 times C1 plus 1 times C1. So that's, times C2. And then 1 times C1, which would be C1, plus 3 times C2, which would be C2. And this is supposed to be the vector B right over here. I mean, this is what I'm supposed to be getting is this, C, is this vector C, which had the components 7, 11. I mean, that's my goal, is that I've created this in such a way that I get the component C, 7, 11 when I'm done. Because what I'm really doing is I'm taking the vector A plus the vector B, and that gives me the diagonal, supposedly C, that I'm working with, the diagonal of my parallelogram. So let's take a look at those component-wise. I can actually create a couple of equations. It should be that this right here equals 7. That is, that 2C1 plus C2 is equal to 7. And it should be that this 11 equals the other component, C1 plus 3C2. So C1 plus 3C2 should equal 11. And after this is high school algebra. So it may have been a little while. You've got a system of equations, 2 variables, C1 and C2, 2 equations, and you should be able to solve one for the other. And you have options, right? So you can use substitution. That means you solve one equation and plug it into the other one. You can do elimination, where you multiply one equation by something and simply eliminate a variable altogether. Either of those options. So you tell me what you want to do. Do you want to use substitution or elimination? Elimination? Which equation do you want to multiply by what number? Which one? Are you talking, Nathan? Okay, which one? The second one? Okay, so how about we do it by -2? Would that be okay? Okay. All right, so my first equation stays the same. So I've still got 2c1 plus c2 equals 7. Second equation is going to get multiplied by -2, so I've got -2c1 minus 6c2 equals -22. What's this going to give me when I add them together now?
-5c2
-15. That's right. What is c2 going to be then?
Negative
I don't think so. +3.
one. Oh,
C2. I think you're already looking back. Maybe it looked at the other one. All right, C2 is 3. Agreed? Okay, if I know C2 is 3, how can I find C1? Plug it in. And I kind of like the equation that I manipulated to be plugging it into because it's already got a C1 without numbers multiplied by it. So I'm going to use that one. This is C1 plus 3 times 3 for C2 equals 11. So what does that mean that C1 equals? 2. Yeah, sorry, didn't hear quite right. Yep, C2 is 2. C1 is 2. So we found out that C1 is 3, C2 is 2. So the answer to my equation, did I write them backwards? I did write them backwards, didn't I? C1 is 2 and C2 is 3. There we go. So my C vector is actually 2A plus 3B. And I'm going to show you how we use that information to actually finish your picture so it makes sense. Okay, you ready? So over here in my picture, what number did I multiply A by in that equation? 2, which means that I'm going to take the vector I have and double the length. So before I went right 2 and up 1, so I'm going to just do it again. Right 2 and up 1 puts me here. So I'm going to extend this vector to here. I think I changed color of purple here accidentally. And what did I do to vector B? Times 3. So I'm going to do the vector B times 3, which means I'm going to do it 3 times. So I've already done it once. So I'm going to go up 3 and right 1, and then up 3 and right 1 again. And if I've drawn this in there correctly, that was awful. Okay, that's not working at all. Let's try it again. I'll do it freehand and carefully. All right, there is 3 times vector B1. I should be able to connect now the ends of my vectors, and I do in fact have a parallelogram. I think it's fairly convincing. It should be a parallelogram. And in particular, you should be able to tell that it is because the sides should be parallel. This side right here and this side should be the same, which means they should have the same rise and run. Yes? And same thing with the other 2 sides. They also should be parallel, same rise and run. Any questions on that?